Okay, this is lecture 8, chapter 13. So as you notice, we didn't finish chapter 12. We went from chapter 12.1 to 13.1. We will come back to chapter 12 to discuss angular acceleration, angular velocity, but for now, we're going to just go to energy. So you should recall this slide we showed at the beginning of the quarter, and essentially we know that work is a force times the distance, and that's equal to 1/2 mv squared minus 1/2 mv initial squared. Now, I'll show you some of these slides, and I may not show them long because I know you could pause this video. And I would, if there's any questions on it, please jot them down because I will review this shortly on Friday also. So this is where we get this from in the first place. We know that we have some of the forces equals ma. So if we dot distance on both sides, which we can do, just like multiplying both sides by some constant or a ds, however you want. Then we integrate that. You see how now we have mass times acceleration over distance, but we know that acceleration ds is equal to v dv. That's one of the early relationships that we found the first week. So by substituting that in, we effectively swap for the velocity, change in velocity. So if we integrate v dv, we just get 1/2 v squared, and then apply it to initial and final. That's where we get the 1/2 velocity squared x plus 1/2 velocity squared y. This is, of course, is in 2 dimensions the way we're showing it. But if we think of it as a single dimension, it's going to be the same thing. You're going to have the velocity of just a single dimension minus the initial velocity. So, and that's what we're mainly going to focus on. And if we do two dimension, we'll just look at the energy in one direction and look at it in the other and treat them as 2 separate items. So this is essentially the basis. Sorry, this is the basis of this whole section. So on the left side, we're going to look at our work done by our forces. And then on the right side, we're going to have our change in kinetic energy. Now, we are going to, when we look at kinetic energy, we are going to then at some point change or add things to the system, which we'll get to. So initially, our equation is going to look like the one written below. U going 1 to 2 is equal to T2 minus T1. And so this is just another way of saying that our energy state from one state to the next is equal to the energy state at the end minus the initial energy state. And that's probably the best way I could think to explain that. So our du then, the u, which is our left side of the equation, is just defined as the force times the distance. But as we recall, the only force that, or the only work done by a force is in the direction. So what we mean by that is if you take a motion and you take a force dotted with its change in direction, then it reduces to this FDS cosine alpha. So the work is a scalar quantity, so that's why there is no direction. But let me pause this, and here we go. Let me do this. Let me stop sharing and show you what I mean. So what we're really saying with the work is if we have a force, so let's say this is our straight line. If we have a force that's drawn at an angle like this, let's say it's 500 newtons, and at an angle of 60 degrees, then if we look at the work done from point A to point B, then the only work is the distance. So let's say it's 3 meters, but the only work that really counts is the work that's in this direction. So obviously the force has a x and a y component, but work done perpendicular. So for example, when this work goes here to here, vertical, that's no work. All right. Whereas if we look at this work, this side of it, then as it goes across, that does do work. So we know that the cosine of 60 degrees is equal to 0.5. So effectively, the work done, our force times distance, which equals our work, or we also write it as U from 1 to 2, is just going to equal 500 times 0.5 for the cosine 60 degrees times 3 meters. So the result then is we get 750 Newton meters, right? So just like a torque is a torque is Newton meters because it's a work, so is this. So essentially all the work that we count up is constituted in this U1 through 2. And so that's kind of a generic expression. It just is a sum of all forces acting over a certain distance. So for example, if I had, let's say I had a block and I slid the block from here to here, then of course the block has a normal force and it's going to have a friction force. And so this goes from here to here, then the normal force does no work during that travel. Okay, normal force does no work because the normal force is perpendicular to the direction of travel, whereas the friction force does do work. And so friction force is a non-conservative force. So we'll talk about conservative, non-conservative. Really, what a conservative force means that it's path independent, whereas a non-conservative force means it's dependent on the path. So obviously you're going to create more friction. If, say, for example, this is your end goal to get here, you could go in a straight line. So your friction is going to be just whatever this distance is, say it's 10 meters. And we know that friction force is equal to mu n. So our total work, or our U, is going to be equal mu n times 10 meters. Sorry about that. Whereas if I instead of doing that, I have a circuitous route like this. So in the end, I have to count for the distance the block went and say that total distance ends up being 25 meters, then obviously my work done from here to here, and let's pretend that it's the same vertical distance, let's say that's 10 meters, but the circuitous one is 25, then of course it's going to be more work to do that. So that's what a non-conservative force is. All right, so let's go back. And so on this slide, that's what that's referring to. So it says, what is the work of a constant force in rectilinear motion? Then we can see that U from 1 to 2, or A1 to A2, is just going to be F cosine alpha times the change in distance. So just as I explained. Oops. Actually, yeah, there we go. Okay, so now we also have work due to change in gravity. And so you should remember this from your physics class, but we know that the change in potential energy from location A to A2 to A1 is essentially the change in height times mass times gravity. So the convention is figure above, when is the work done by the weight positive? It's when you move downhill. So Y2 to Y1 is positive, whereas when you go uphill, it's negative. And that's just a sign convention we use. So it takes input, obviously, to go uphill, whereas downhill, it's you're gaining potential energy. So think of gaining as being positive, as you're gaining potential energy as you go up, you're gaining kinetic energy as you go down. Okay. But whenever you go down, then that's essentially you are, wait, sorry, my slide's doing something. Yeah, just to summarize, if you go down, it's positive. If you go up, it's negative. Sorry, this is not going to be an award-winning video. I can see that now. All right, so then we go on to springs. So when we have springs, we deal with kinetic, a change in potential energy, which can be converted to kinetic energy. And you probably remember this too. So if we take the change in U, or potential energy, that's equal to force times the change in distance, dx. So we know the force is equal to negative kx, which is k being the spring constant. So we're going to assume we're dealing with springs that obey Hooke's law, where they're linear. Most springs don't, but for our class, we're going to assume they do. And then we have our U1 to 2 for springs, which is that. Okay, so one convention too is work of the force exerted by a spring is positive. So that means that when you compress a spring, that's going to give negative work. So stretching a spring is negative work. Compressing a spring is positive work. So that's the sign convention for that. So what I would be, the main parts to take away here, besides these are slides out of your book, is I would look over the reading just to make sure you understand. I'm not going to test you on the origin of these, but the origin of this is similar to how we got the 1/2 mv squared also. And then we have this equation here, which is just saying that the work of the force exerted by the spring is equal to the area under the curve. And so if we take the whole area under the curve, so if we were given a plot of force versus distance, then you could determine the work done, and it would be in force times distance, so the units would work. Okay. So here's a question then, kind of already answered it, but as the block moves from A0 to A1, is the work positive or is it negative? So we know that if you're stretching, it's going to be negative. And then in the second one, if the block moves from A2 to A0, or to A in this case, either way, then it's compressing. So we know it's positive. All right. So here's a kind of a summary of everything with the highlighted stuff. So we know that the right side equation is the change in kinetic energy. So we can write T2 minus T1. That's going to be your 1/2 mv1 squared. And so then we know the left side is the equation, is the work done by forces on the body, but it can also be, and it's I guess in this case we're just doing work, and so we'll treat the other ones, gravity and spring potential energy. So what we end up with, and this is the important part, is we get up with this total equation down here. We have the spring, the spring kinetic energy, which is E2 and E1. We have the gravitational potential energy, and then we have U1 to 2, the state, and this could be for non-conservative forces. So this would be your friction that I described earlier. All that's going to be the total change in kinetic energy. So it's really, don't overcomplicate it. I just think of it as like a bank account. So you have so much energy in your bank account, and you're either going to add it or take it away. And so you're really looking at the state, the final state, and then you're looking at the initial state. So the initial state, you start off with so much spring energy, so much kinetic energy, so much potential energy, and then you progress to your second state or final state. And then did you gain potential energy or did you lose it? Did you gain spring energy or did you lose it? Did you gain speed or did you lose it? Did you move across a path with friction? Then that's energy that was expended. So that in the final 1/2 mv squared of the kinetic, it could be as simple as that being 0. For example, if you had a car moving at 80 meters per second and the car slams on the brakes and skids to 0, then you can determine, if you assume all the energy went into the friction, then you can determine how far the car skidded, assuming that you know friction coefficient and n. I mean, it's a simplified way of doing it. And there's, there's other factors, but for our first R class, we're going to limit it to that. We're not going to look at anything outside of it. All right. So here's a question. Block A is released from rest, slides down the frictionless loop. Maximum height H of the loop is the same as the initial height of the block. Will A make contact? Will A make it completely around the loop, or will it lose contact with track? So we know that if it starts at A, when it gets to A over here, assuming there's, in a perfect world, it would have a velocity of 0. So it's not going to be able to go past that. If this was slightly lower, then yes, but the fact that it's at the same height means that when it reaches this point, and I mean, I guess you could say H is up here, not there, but I think the point is that it's going to reach the same and it's going to fall. All right. Then we have another question. We have two small balls, A and B, with masses of 2m and m, and we drop them. So how is that going to relate with kinetic energy? So, well, in both cases, we know that kinetic energy is 1/2 mv squared. So if we were to look at the equation, 1/2 mv squared, then both are going to have the 1/2, both are going to have the same velocity when they hit. So the v squared is going to be the same. So the only difference is one's 2m and one's m. So the answer is you're going to have double the kinetic energy for B. I think I said that backward. I meant you're going to have A is going to have double the kinetic energy because it has twice the mass. Velocity will be the same. So that's the only difference is the mass. So of course we know if it was double the velocity, then it'd be 4 times. But okay, good. So let's do a couple examples. And this is, I think, probably one of the easier topics because as long as you just, like I said, keep it like a bank account, keep track of your pluses and minuses in terms of the different types of energy, then you should be fine. So we have this here. So we'll start off, we have a 2,000 kilogram auto, starts from rest. Well, I'll let you read it. You can pause it, and then we'll go ahead and do the problem. So our object's moving down. So let's go ahead and go to the sheet. So here we have our, hope that's not too glary. So we have our car, 2,000 kilograms, rolls to B, applies the brakes. We're not skidding though, we're impending, skid, and then we stop at C. So that's 30 meters later. Okay, so we want to essentially find the final velocity at B. So we want to find how fast, what is V? So we know we have V naught here, we have V at B, and then we assume that V final is 0 there. And so, yeah, it looks better. And so first off, we'll look at A. So A is just the velocity at B. And so don't overcomplicate these problems. So our equation, remember, it looks like U1 to 2 equals T2 minus T1. All right, so a lot of times you're going to write it as T1 plus U1 to 2 equals T2. So if we do that, we know that T1, right, is T1 is kinetic energy. All right, so we know that the car starts at rest. So if V naught initial velocity is 0, so we know that we have no kinetic energy. So we can say that's 0. So really, if we think about it, we're assuming when we're rolling, again, there's no rolling friction. It's just change in potential energy has to equal kinetic energy. So we know that we're going downhill. So it's mgh, right? Mass times gravity times h. We know that h is equal to the delta y, all right? Or y2 minus y1, all right? So we're given that is going to be what? It's going to, h is going to give us 150 meters sine, I get rid of the meters, but it's going to be 150 sine 6 degrees. Okay, so that's where we get that from. Now, if we set this, that's there, and then we go ahead and we set this equal to 1/2 mv squared. You may remember this. Mass doesn't matter in this case because really the velocity, when we solve for it, is just equal to the square root of 2gh. And you probably remember this from your physics class. So with that, we can just plug it in and we get v at b is equal to 2 times 9.81 meters per second squared, and then times the height, which is going to be 150 meters times sine 6 degrees. And then that's all to the 1/2. So meters, meter squared, second squared, square root gives us meters per second. So we find that VB gives us a value of 17.54 meters per second. So that's how fast it went, just from the change in kinetic energy. So pretty easy. All right. So then we also want to know our final friction. So we need to look at that. And so with that, we're really looking at just the change in the overall potential energy and how much friction is involved in that. So what we get for part B, okay, is we look at it as, here's we are starting here. We're going to have a speed there, and then we're going to stop here. So what we need is a friction in that, a friction coefficient. So we're going to find mu. Okay. So really it comes to be, since T1 is 0 and this is 0, then, and we only impend our brakes this far, then we start with no kinetic energy, we end with no kinetic energy. All right. So we end up with U1 to 2 equals mgh, but we also have force times distance. So what we're really looking at in this problem is both of these are on the same side, because we started with T1 plus this, and let's just rewrite it. So T1 plus U1 to 2 equals T2. Those are both 0, so that's not right. Well, U1 to 2, remember, U1 to 2, that accounts for mgh, 1/2 kx squared, and force times distance. So all those phenomena are lumped into this term. So really what we have is all of it is going to be equal to 0, but we can write it as one equation. So what we're going to write is the mass times gravity times h is going to minus the force times distance is going to equal 0. So that's what we're doing here, because we know this all has to, because that's 0. So if we expand that, then we know mass times gravity times h, because we do have to, the fact that now this is one way to do it. You could have just used the velocity that you calculated up here to figure out how much kinetic energy you had moving along here. That's another way. So I'm not saying this is the only way. If you think that would be easier to convert that to energy and then set that energy to the force times distance. Just remember that you also have to include, if you did it that way, this little extra downhill that you had. So it'd be a more complicated problem, because you'd have 1/2 mv squared plus the mgh minus the force times distance. So I find this way a little bit more straightforward. We have the total change in potential energy. And in order to stop that total change in potential energy, we need a friction force times distance. So if we fill in our numbers, we just have our 2,000 kilogram car times gravity. And then our height is a total distance of 170 meters, right? 30 plus 150. So 150 and 30. So 170. That's 20 meters. I apologize. That's not 30. Silly me. Yeah, it's 20 meters. I thought that looked strange. So 170 and then sine 6. And then subtract from that 2,000 times 9.81. And so what is this? This is the normal force, right? Normal force of the vehicle. And then the normal force times cosine 6 degrees, right? So it's just mg cosine 6 gives us the normal force. And then the normal force times mu. And then the distance, right? So here's this is force. And then times 20 meters. So force distance. So and for F just equals mu times normal force. Okay. So we get 384,644 minus mu times 390,250 equals 0. So mu equals 0.89. Okay. So hopefully that made sense. Let's do another example. Okay, so let's look at this example. So here we have a trailer truck. So the truck's moving, it's at 72 kilometers per hour. And then it goes ahead and it increases speed until it's at 108 kilometers per hour. And it does that in a 300 meter distance on a grade of 2%. So over 300 meters, 2% of 300 would give us a rise of 6 meters. So we could calculate the angle, obviously, using tangent, 6 over 300, but we don't need that. We just need the change in height. So that's 6. So we're given the mass of each, and we want to then determine the average force at the wheels of the cab. So really, it's a force times distance problem. Don't worry about the individual wheels, the fact that there's 18 or whatever. We're just looking at what is the force on the entire truck. Remember, we're still in particles, so just treat the truck as a particle. And then we want to know the average force on the coupling. And so that's just going to be the fact that the forward part of the truck is pulling on the back. And so we'll have to account for that. But essentially, it's very similar. So let's go ahead and stop share. So here we have what we need. So we're going 20 meters per second to 30 meters per second. So that's what the kilometers per hour changed to. We know that our rise is 6 meters. So 2% of 300 meters. All right. And we know the mass cab equals 1,800. And the mass of the trailer is 5,400. All right. And so let's go ahead and look at it. So now we know the total weight is going to be, so W is just going to equal the sum. So that's 7,200 kilograms. So 7,200 times G. So weight gives us a value of 70,632 newtons. Okay. So let's look at first the average force on wheels. So A, force on wheels. So in that case, again, we have T1 plus U1 to 2 equals T2. So we're not given any friction. So really, what do we have? We know T1 is our kinetic energy, so 1/2 mv squared of the whole system. And then plus, now what is our, we know it's the force of the truck times distance, right? So Ft times d. And then, but we're going uphill, so we're losing potential energy. So we have to subtract. Well, we're gaining potential energy, but it's a negative. So I know that seems kind of counterintuitive. But as we go up the hill, we subtract it. And I guess the best way to think about subtracting it is the fact that as we go uphill, whatever force we're putting in there, we're not, it's obviously taking some of this force times distance to get us to go up the hill. So it's going to take away from this total amount. So just like a bank, this is costs us energy to go uphill. So minus mgh, and then that all gives us 1/2 mv final squared. Call that initial. And that's it. So then it's just a matter of doing the algebra. And so if we simplify, we get the force of the truck equals, and I just factored out 1 over distance, and that's going to be 1/2 mv2 squared minus 1/2 mv1 squared plus mgh. All right. And so then we can also factor out m. So we get force on truck equals m over d, and then 1/2. And then now we can plug in v2 squared minus v1 squared. And then that's just going to be plus gh. So if we plug in our numbers, we have 7,200 divided by 300. And this part, you'll probably fast forward because I know you guys can do this, but just in case, 1/2, 30 squared minus 20 squared plus 9.81 times 6. All right. And so we end up with Ft, so our F truck gives us a value of 7.41 times 10 to the third kilonewtons after I convert it. Okay. Sorry about that. So there's that. All right. So to do the coupling, the force pulling on the hitch, that's just a little, it's a little different. In that case, it wants to know, what force is required. And so in that case, we're going to look at it. It's a similar equation. So again, we have 1/2 mv1 squared plus the force of the coupling times the distance, and then minus mgh, and that equals 1/2 mv2, or final squared. So I should use 1 and 2. That's typically, so m1, v1, v2. Yeah, so that's a 2 if you could, 2. So we have that. So if we go ahead and substitute, and really we're solving it the same way, but the only difference now is we're changing our mass to 5,400. So mass equals 5,400. That's the difference. Because what it wants to know is what is the force on it. So before, we already had, we were looking at the entire system, but the force on the coupling, this was the force on the wheels, this is the force on the coupling. So the coupling, of course, is what connects the truck. So if you have, you had the wheels push it up this distance. So imagine that you have a trailer tractor at the back, and that weighs 5,400. And then you had a force like this, right? So that force times that distance. And so everything else is the same. And the only difference is that, like I said, we just put mass in at 5,400. So that problem, it maybe an easier way to understand it would be if I was pulling this trailer up a hill, and let's say I was, very strong and I could pull it up the hill, then how much force would I have to apply over that distance? And that's what this is. So over 5,400, I'd have to use this, using that mass and plugging it all in here again like before, I'd end up with 5.56 kilonewtons. So if this is my kingpin right here, kingpin, which is that's the pin that connects to the connector. I can't remember the name of the actual part that they connect at the back of the truck, but I know this is the kingpin that comes off the trailer, and then that connects into this little piece here, and then the fifth wheel, I think it's called the fifth wheel, and it connects into here, and then so this is the force that's being put on that pin while it's moving in this time. Because normally we'd think of this pin as having no force on it when it's at a constant velocity. It would be sitting in there, but only when we accelerate or brake is it going to pull or push. So this stuff comes in important later on, because if you're a designer, you have to think about how much force is this? What's the maximum force this thing's going to feel? How quickly can a truck actually accelerate up a hill? And then you put a factor of safety on it, because you don't want this thing to bend in half or fracture and then leave half your load or the whole load behind. So this is kind of where the dynamics meets the material science, which is more my avenue. But nonetheless, I think that hopefully that makes sense. But again, we got a good estimation based on what was there. All right. Okay, so I was going to do this, but I think I'm going to do this on Friday in class, because there's some aspects to it. I want to be able to physically see your reaction and answer questions to it. So we'll do this one on Friday. So that's pretty much what I would have been able to do in one lecture period. Again, thank you. Sorry, I know this isn't the ideal situation, but I figure it's better than nothing. So hopefully I plan to be back Friday unless things get worse, but I'll somehow drag my butt in there. But okay, well, thanks everyone for listening, and I'll see you soon.